Okay, let's jump right into it. Today in the deep dive, we're tackling some really big questions, maybe the biggest.
Mm-hmm.
What are the fundamental limits of, human knowledge? And why do some of the deepest physics mysteries make us wonder if we can ever truly get a complete picture of the universe?
Right. It's a strange place to be because, look, we've made incredible strides. We have these amazing models from tiny particles right up to cosmic structures.
Yeah, the progress has been amazing.
But right at the edges where we're pushing, we hit these puzzles, real head scratchers that make you question if a final single theory is even, well, achievable.
And our guide for exploring this today is Dr. Alexei Semikhatov, a leading physicist. He asks this blunt question: are scientists in a dead end? Why can't we understand the universe completely? So we're really digging into his perspective.
Yeah, and it's not about being defeatist, It's more about an honest look. Where do our best scientific ideas just stop working? It's kind of an invitation to think about the philosophy behind the physics, too.
Absolutely. And the source material gives us this almost unbelievable starting point. The universe is fine-tuning.
Ah.
Our whole existence seems to hinge on these fundamental physical constants being set with just staggering precision. Semikhatov calls it a balance of constants. Almost feels wildly lucky.
It does. And what's weird is that fine-tuning, it's like a synonym of knowability.
How so?
Because the universe follows laws that are simple enough, effective enough for us to even discover them in the first place. Science could happen because of that simplicity. But that very luck, that fine-tuning, points to something deeper we just can't explain yet.
Exactly. It's a paradox. The knowability itself hints at unknowability. And as we push deeper, we find these complexities, these disagreements between our best theories.
Yeah.
It really suggests there might be hard limits.
So that's our mission for this deep dive, right? We'll journey through some of these big ideas. String theory, the Anthropic principle, quantum weirdness, the search for a unified theory.
Yeah, lay out the challenges.
And see what they imply philosophically about this whole quest to understand everything.
Okay, let's really get into that fine-tuning, this balance of constants.
Yeah.
What does that actually mean for, the stuff around us?
It means those basic numbers, gravity's strength, the electron's charge, how heavy particles are if you tweak them, even just a tiny bit.
Uh-huh.
The whole possibility of complex things forming just evaporates. No stable atoms, no long-lasting stars, certainly no life as we know it. Semikhatov says, our universe came to us with constants set in it. We do not know why they are like that.
They're just givens.
They're just givens, exactly.
Yeah.
We don't know the underlying reason why they have those specific values.
And the source has some really vivid examples of how tight this balance is. The electron's mass, for instance.
Yeah, if the electron was, say, a bit heavier compared to other particles, the way atoms bond, chemistry itself would be totally different. Our kind of complex biology, probably impossible.
Or that tiny mass difference, right, between a proton and a neutron.
Oh, that's crucial. Change that by just a small percentage. Stable atomic nuclei just don't form, period. No nuclei, no atoms, no us.
And gravity, the big shaper of the cosmos.
Right. Make gravity a little stronger. The universe collapses back on itself too quickly, a little weaker. It expands too fast for stars and galaxies to even form. You wouldn't get those nice, slow-burning stars you need for life to have a chance.
And there's the fine structure constant, too, that relates to electricity and magnetism.
Yeah, that dimensionless number basically governs how atoms interact with light, how chemistry works. Change it, and you mess up everything from galaxy formation to the nuclear fusion inside stars that creates heavy elements.
Heavy elements like
oxygen, carbon, nitrogen, phosphorus, the stuff we're made of, the stuff planets are made of.
Yeah.
It all depends on that constant being just so.
Wow. Okay, so the massive question hanging over all of this is,
Yeah.
given that we exist on this razor's edge, why is the universe so tuned for us? That's the core puzzle.
That's the elephant in the room for physics, yeah. A huge question mark.
So one huge attempt to answer that why, to explain why the constants maybe had to be this way, was string theory. What was the big dream there?
The dream was, well, huge. To unify everything, all the fundamental forces, gravity, electromagnetism, the nuclear forces, and all the fundamental particles into one single beautiful theory.
And the idea was particles aren't points.
Exactly. Not points, but tiny, vibrating, one-dimensional, well, strings. And the different ways these strings vibrate, that's what gives us the different particles and forces we see, like different notes on a guitar string.
Okay, but this needed more dimensions than the usual 3 space plus 1 time.
It did, yeah. String theory naturally seems to require extra spatial dimensions, usually 10 dimensions in total.
So where are the other 6?
The idea is they're curled up into something so small we just don't see them in everyday life. He uses the water hose analogy.
Right, the garden hose. Looks like a line from far away.
But get closer, and you see it's got thickness, a circle, it's actually 3D. Those extra dimensions are supposed to be like that hidden structure, curled up incredibly tightly.
And the way they were curled up, that was supposed to be the key to explaining our specific universe.
That was the hope. The geometry of how those extra 6 dimensions are curled, these complex mathematical shapes called Calabi-Yau manifolds, that geometry was supposed to dictate the fundamental constants in our 4D world. Particle masses, force strengths, everything.
So for a while, people were really excited.
Oh yeah, there was a peak of enthusiasm. The hope was string theory would spit out our universe's properties uniquely, just from the math.
Oh, yeah, that hope hit a snag.
A big one.
A colossal one, yes.
Mm-hmm.
As they dug into the math, they realized there isn't just one way, or even a few ways, for these dimensions to curl up consistently.
Uh-oh.
There are, well, an absolutely mind-boggling number of possibilities. The estimate is around 10 to the power of 500.
10? With 500 zeros. That number doesn't even feel real.
It's unimaginable. Semikatov points out, 10 to the 100 is already way more than all the particles in the known universe. We're adding 400 more zeros. Okay, so what did that do to string theory as a theory that could predict our physics?
It pretty much killed that aspect. This huge number of possibilities, the landscape they call it, means the theory completely lost predictive power for our specific universe.
Because it could describe almost any universe.
Pretty much. If your theory can generate universes with almost any combination of constants, and you don't have a rule to pick our specific configuration out of that massive landscape, well then, measuring our constants doesn't confirm your theory. It becomes not falsifiable.
You can't prove it wrong.
Right. Whatever you measure, somewhere in those 100 and 500 possibilities, there's probably a universe that fits. So it stops being predictive science in that sense.
And what does Semikatov call that moment?
He calls it the beginning of the end for string theory's dream of being the theory that uniquely predicted our world physics.
So string theory didn't just vanish, but its role changed. What's the takeaway?
I think the key insight is that even an incredibly elegant mathematical structure aiming for unification might not be enough to pinpoint our specific reality. It really underscores how vital experiments are, even for fundamental physics, and maybe unintentionally.
Yeah.
It gave a lot of theoretical momentum to the idea that maybe our universe is just one of many possibilities out there.
Which leads us perfectly into the Anthropic principle. This feels like a response to both that fine-tuning puzzle and this landscape idea from string theory.
It is, yeah. The weak Anthropic principle, the most common version, offers a kind of straightforward, almost logical explanation for fine-tuning.
Okay.
It says, look, if there are a huge number of universes out there, maybe those 1,000, 500 string theory possibilities, maybe others, and they each have random physical parameters.
Then most of them would be duds.
Exactly. Most would be totally unsuitable for life. They might collapse instantly or never form atoms or have stars that fizzle out or just be chaotic messes. In those universes, there's simply no one to ask this question about why things are so finely tuned.
So we see our universe the way it is.
Simply because these are the conditions required for observers like us to exist and ask the question in the first place. We couldn't possibly observe a universe where we couldn't exist.
So it's less about why the constants are what they are and more about why we find ourselves in a universe that works for us.
Precisely. Semikatov uses an analogy. It's like asking, why was I born to my parents? It explains your existence given those parents, but it doesn't explain the fundamental why of that specific family existing.
And how does he rate this as a scientific explanation?
He's pretty critical. He explicitly calls it not a physical theory, but a moral philosophical concept.
Ouch.
Yeah. He sees it as maybe frank speculation or out of frustration, almost like a comfort for the poor, a way to sort of turn defeat into victory when science hits a wall and can't actually calculate those constants from first principles.
And the big scientific sticking point is, you can't test it.
Fundamentally, yes, it's non-falsifiable. There's just no possibility to clarify anything about these other hypothetical universes it relies on. Science needs things you can check, repeat, observe.
Reproducible, can return and check.
Exactly. So explaining things in our universe by pointing to countless unobservable universes, that steps outside what we normally call empirical science.
Semikhatov also frames this anthropically tinged view as another step in humanity's long exercise in modesty.
He does. It's a neat historical perspective. We thought we were the center of the tribe, then maybe just one nation.
Then not the center of the solar system.
Then just one solar system in a galaxy, one galaxy among billions. This anthropic thinking kind of extends that modesty to an inter-universe scale. We're not special because the cosmos was made for us. We're just in one of the universes where observers could arise, out of maybe countless sterile ones. We won the cosmic lottery, maybe.
That really flips the perspective, doesn't it? It changes the question from why is our universe like this to maybe why are we in this kind of universe? What stands out to you about that kind of shift?
For me, it really underlines how our cosmic address keeps getting smaller, less significant in a way. It forces you to confront whether our existence is some unique miracle or just an expected result if you have enough cosmic dice rolls.
Yeah.
It really blurs the line between physics and deeper philosophical questions about existence.
Okay, let's shift gears from the cosmic scale down to the very, very small. Quantum mechanics, which has its own deep, baffling conceptual issue, the measurement problem.
Oh boy, yeah. This is where reality gets fundamentally weird. Quantum theory says particles can exist in superposition, meaning they exist in multiple contradictory states at the same time. Like, an electron isn't just spinning one way or the other. It's described as being spin up and spin down simultaneously. Semikhatov has this image of a charmed magnet that, before you measure it, is pointing always at once, but the moment you look, it instantly snaps to align perfectly with whatever direction you chose to measure.
So we never see that superposition, right? When we actually measure, we always get a definite answer. Spin up or R spin down.
Exactly. That's the core paradox. The main equations of quantum mechanics describe how these superpositions evolve smoothly over time. But the act of measuring seems to force this sudden, abrupt jump into just one state. It's called the collapse of the wave function.
And this collapse, it's not explained by the basic quantum equation.
No, it's kind of bolted on. Semikhatov calls it a miracle in the standard view, a moment where it seems like the fundamental law is violated. It's deeply unsatisfying, theoretically.
Okay, so
Yep.
enter the many worlds interpretation, MWI, Hugh Everett's idea. This is a radical fix.
It's definitely radical, MWI says. Forget the miracle. The fundamental quantum laws are never violated. The wave function never collapses.
So what happens then when you measure?
Instead of collapsing, the entire universe, you, the measuring device, the particle, everything divides into two components, or more accurately, it branches into multiple, completely separate, parallel universes.
Whoa. So if the electron could be spin up or spin down.
One whole branch of reality becomes a universe where it is spin up, and another whole branch becomes a universe where it is spin down. Both possibilities become real, just in different worlds.
So Schrodinger's cat.
Is genuinely alive and dead, just in different non-interacting branches. And we, as observers, we're also split. We only experience one of those branches. This implies, as Semikhatov puts it, quite a non-small number of parallel worlds branching off constantly everywhere with every quantum interaction.
Okay, that sounds philosophically heavy, especially with probability.
It's a huge challenge. If every possible outcome actually happens in some branch, what does probability even mean anymore, beyond just predicting our local experience? If everything will happen anyway somewhere, does it diminish the significance of our choices? Does it mess with free will, responsibility? It's hard to even know how to assign weight or importance to these different branches if they all exist.
But mathematically, MWI hangs together.
That's one of its main selling points. It's a mathematically consistent way to deal with the measurement problem. It lets you break through some tense place, incomprehensible place, unexplained quantum mechanics, as Semikhatov might say, by getting rid of that awkward, unexplained miracle of collapse.
So the trade-off is accept mathematical neatness, but embrace an unobservable proliferation of universes and fundamentally question things like probability and choice.
That seems to be the deal, yeah. It really pushes us to define what we mean by understanding in physics. Is it just math that works? Or does it need to be testable or even intuitively make sense? Semikhatov mentions the 100 years of understatement in quantum mechanics. We've been wrestling with these core issues for a century.
And you mentioned a moral side earlier.
Well, yeah, if you really take MWI seriously, the idea that everything will happen anyway in some branch, it could potentially undermine our usual reasons for striving, for making choices based on desired outcomes in this reality we perceive. It leaks out of physics into moral philosophy, potentially shaking up how we think about our lives and decisions.
Okay, so we've got these hints of multiple universes popping up from string theory's landscape and also from this many worlds interpretation of quantum mechanics. But Semikhatov draws a very clear line about the scientific status of the multiverse concept itself.
He does, he's quite direct. Another universe, by definition, is something that quickly ends up outside the scope of science.
And the reasoning is fundamental separation.
Yeah. There's no known way these proposed universes could be connected by a single time and single space. It's not like hopping in a spaceship to another galaxy. Inter-universe travel or communication. It's conceptually completely different and seems impossible by known physics. And science, fundamentally, needs stuff you can interact with, test, check.
Reproducibility can return and check.
Exactly. And with these other universes, there's no possibility to clarify anything through observation or experiment from our side. They remain hypothetical.
Which is why the anthropic principle gets labeled philosophical, not scientific.
Precisely. Because its explanation hinges on these unobservable universes, it becomes untestable by the scientific method.
Semikhatov also brings up a pretty frightening hypothetical if somehow universes could interact.
Right, it's a stark thought experiment. What happens to your electrons, he asks, the ones you're made of, when they suddenly find themselves in another universe?
Uh-oh.
The terrifying implication is they'd suddenly be in a place with potentially different physical laws, or maybe just a different fundamental vacuum state.
And vacuum state isn't just emptiness.
No. In physics, the vacuum is teeming with potential. It's the ground state of quantum fields that generate particles. And it's thought these vacuum states could be physically simply different in other universes, or even in different regions of space-time. Our vacuum is stable for us, but maybe not the only possible stable state.
Which leads to vacuum bubbles. That sounds bad.
It sounds extremely bad. The idea is if a bubble with a different vacuum somehow formed maybe a quantum fluctuation, maybe bumping into another universe, it could expand outwards at the speed of light.
And inside the bubble.
Hellish restructuring. A phase change so fundamental that all matter at the level of electrons and quarks would just turn into something else. It wouldn't be our kind of matter anymore. It'd basically be the end of the universe as we know it, at least wherever the bubble expanded.
Okay, that's cheerful. And
Yeah.
what about calculating the odds of that happening?
Semikhatov basically dismisses it. He calls trying to calculate that probability an absolutely stupid occupation.
Why? Because the math is too hard.
Not necessarily. It's because the theories that even suggest such possibilities, like the string theory landscape giving different vacuums, those theories aren't actually confirmed or tested in our universe. So calculating probabilities based on unverified, speculative frameworks, he sees it as scientifically meaningless.
So, pulling back, the key point about the multiverse from a scientific angle is
It's that while these ideas arise from deep theoretical thinking, they remain largely outside empirical science as we currently know it. They're theoretical possibilities, maybe interpretations, but not proven realities like planets or stars. They belong more to philosophical discussion or even sci-fi because we just don't have the tools to scientifically verify them.
okay, putting aside those more speculative ideas, what's maybe the biggest, most concrete roadblock right at the forefront of physics today?
Ooh, that's got to be the failure so far to unify general relativity and quantum mechanics.
The two great pillars.
Exactly. GR gives us gravity, the cosmos, big stuff. QM gives us the small stuff, particles, the other forces. Both work incredibly well in their own domains. But, as Semikhatov says, they unfortunately do not agree with each other fundamentally. Especially in extreme places like inside black holes or at the Big Bang. They just give conflicting answers.
And this isn't a new problem they just noticed.
Not at all. This has been the big challenge, the ultimate role for, 50 years or more, almost 100, depending on how you count. And we still don't have a theory that convincingly brings them together.
String theory tried.
It was the leading contender for a long time, yes. But as we talked about, it kind of did not prescribe itself to our universe in a unique, testable way that solved the unification problem cleanly.
So the fact that we still don't have a working theory of everything after all this time, that's a major sign we might be missing something really fundamental.
It strongly suggests that, maybe our current ways of thinking, our mathematical tools, just aren't up to the job of describing reality at that deepest level. It could be what you might call an epistemological wall, a limit, maybe not in the universe itself, but in our ability to grasp it with our current science.
Which brings us back to Semikhatov questioning the whole idea of reaching a final theory of the universe.
Right. He floats this alternative view. Maybe the goal isn't some single ultimate equation set. Maybe, he suggests, world maybe, we are just getting to know the world better and better, endlessly.
Like peeling an onion, cutting off layer by layer.
That's the metaphor, yeah. We found Newton's gravity worked great. Then Einstein's GR came along, worked super better for cosmology. We have QM for the small scale. But what else might there be? Maybe we're not converging on one final answer. Maybe we're just continually uncovering deeper, perhaps infinitely nested levels of reality.
So the universe itself might be infinitely deep and infinitely complex.
That's the possibility this perspective opens up. It's a real shift from the old classical dream of a clockwork universe you could fully map out. Understanding, in this view, becomes a journey without a final destination, a continuous process of discovery.
It reminds me of that quote from Newton about feeling like a boy playing on the seashore.
Finding pretty pebbles while the great ocean of truth lay undiscovered.
Yeah.
It's a perfect fit for this viewpoint. The mysteries and the unanswered questions aren't failures. They're the ocean. They're what keeps science moving forward, pushing us to deeper, even if never absolutely final, understanding.
So wrapping up this deep dive then, Semikhatov suggests our universe is, more or less knowable. We got super lucky that there are simple, effective laws we could discover it all.
But alongside that luck, it seems there are these profound, maybe inherent limits to how complete our ultimate understanding can ever be.
And all these things we've talked about, the fine-tuning mystery, string theory's landscape problem, the philosophical edge of the Anthropic principle, the weirdness of quantum measurement, and many worlds, the speculative multiverse, that stubborn unification problem.
They all kind of point to this ongoing exercise in modesty, don't they? Something maybe built into the very nature of doing science at the deepest levels.
His final thought really stays with you, that the ultimate goal, the highest value, might not be finding that final complete theory.
But rather, it's found in the process itself, the passionate, ongoing investigation, realizing, as he puts it, the highest good of our mind, which is trying to understand the universe, and through that, understanding our connection to it, our unity with it, even if the absolute final truth remains just out of reach.
Wow. We've certainly covered some mind-bending territory today. From the universe's uncanny fine-tuning to string theory's unexpected turn towards a landscape of possibilities, the philosophical tightropes of the Anthropic principle and many worlds, and that persistent quest to unify physics.
Yeah, these frontiers really do suggest that the universe might not be a puzzle with a single solution we can find. Maybe it really is infinitely deep and infinitely complex, always holding more layers for us to try and understand.
So here's a final thought, something for you, the listener, to chew on. If this quest for knowledge isn't about reaching a final answer, but more like an endless peeling of an onion, cutting off layer by layer, and if our place in it all is part of this constant exercise in modesty, how does that shift your perspective on what it really means to understand the universe and perhaps to understand ourselves within its vast, still unfolding story?